Now let's look at another function. In this case, we're going to be dealing with the question of what if our function is discontinuous. The previous one, it was just an increasing line, at least in the smallest period, that kept repeating itself. Here we're going to come into contact with a discontinuous function, and we want to, again, find the Fourier series expansion of the function. All right, so step number one, we want to identify that smallest repeating part of it. Again, it's given to us graphically, so we can see we start at 0. We're going to go over. This is at 0.5 seconds. It's going to jump up to x is equal to 2, and it's going to be constant until 2 seconds, drop back down, dwell at the bottom for 0.5 seconds, jump up, rest there for 1.5 seconds, come back down, etc. So this sawtooth pattern keeps repeating itself. We have 1, 2, 3, 4, 5 repeats of this same 2-second pattern. So our fundamental frequency is going to be determined by our smallest period. In this case, 2 seconds is going to be the smallest period that we can copy and paste it over and over and over again. So we only need to look at, to establish our equation for step number 2, just look at the first 2 seconds and let's see what that is. All right, so if we see here, now it's just constantly a value of 0, then it jumps up and that's constantly a value of 2. However, there's this, it changes over at 0.5 seconds. So we can express this as a piecewise function, a pretty simple piecewise function because it's constant, but it jumps to a different constant value. So we can say, in a piecewise terminology, it's 0 if our time is between 0 and 0.5 seconds, so that's this dwell down here, and then immediately it jumps up to 2 from 0.5 seconds to 2 seconds. And that's all it does, and then it's going to keep repeating. But remember, for this x of t, when we're doing an analytic Fourier series expansion, just look at that smallest repeating pattern. So in this case, that first 2 seconds. Now, take note of how I defined it here. Notice that I say that the first part is from 0 to 0.5 seconds, and the second part exclusive. But for the second leg of it, it's 0.5 inclusive, so it is 2 at 0.5 seconds until 2. It really doesn't matter for this purpose if I say it's 0 at 0.5 seconds or if it's 2 at 0.5 seconds when I'm doing the Fourier series expansion, and we'll see how that works in a second. So whether I define it less than or equal to down here or less than or equal to up here, it really won't make a difference for that instance in time at all when we do the Fourier series expansion. Right? And again, we can use our period of 2 seconds, so our omega value is pi, since it's, again, 2 pi over t, which is 2 pi over 2, which is just pi. So pi radians per second is the fundamental frequency, and this is how we can express our equation. So this is our step 1, this is our step 2. We have a functional definition of our function on our smallest period. Now we can go and find our coefficients, just like we did for the previous example. So we'll start by finding our value of x naught. So again, copied up our now piecewise definition, and we'll go to our definition of finding a naught using the period. That is unchanged, but what is different now is my value of t is now pi, and my x of t is this piecewise function. So I can write this as, over here, 2 integrals. Remember, we can split an integral up. So instead of saying it's, I can start with saying it's the integral from 0 to 2, which is what I need to do, but the integral of any function from 0 to 2 is the same as the integral of our function from 0 to 0.5 plus its integral from 0.5 to 2, or however many of these that we need. So splitting an integral up, there's nothing wrong with that. We can do that for any type of function. The reason it's helpful for a piecewise function like we have here is because I want to integrate x of t from 0 to 0.5 plus the integral of x of t from 0.5 to 2. Well, as long as x of t is consistently defined on each individual integration, then I can do really just one line of my piecewise function at a time. So x of t does have one definition from 0 to 0.5. It's 0 in this case, but I can now just sub in 0 here as long as I'm only integrating in the range where that's my value of x of t, which is 0 to 0.5. So it's 0 on that entire range. Now, if I go to my second piece, I want 0.5 to 2, the integral of x of t. Well, on this interval, 0.5 to 2, I have a consistent but different consistent value for x of t. It's just 2. So I can make this second integral here the definition of x on my second interval. All right, so this is helpful because now it's, in this case at least, pretty easy to do my integration. The integral of 0 is just going to be 0. This 2 over 2 is going to go to 1. So all I'm going to be integrating is 2 from 0.5 to 2. So I can take the antiderivative. The antiderivative of 2 is just going to be 2 times t. Or if I really wanted to, I could pull the 2 out of here and it's just dt. And the antiderivative of dt is t. So however you want to slice it up. So the antiderivative of, well, this is just going to be 0. I don't need to do its antiderivative. And then the antiderivative of this second term is going to be 2 times t. And evaluated at the top minus evaluated at the bottom. So my a naught value is going to be 4 minus 1, which is just 3. So going through the integration steps, we get the constant value for our a naught term is just 3. Now we can proceed and find the an and then the bn. And we're going to use the same idea of, if we have a piecewise function, we are able to split the interval of our integrals to aid us in doing the integration. Right, so moving on to our an term now. Again, we have that definition from before. And now we're going to split it. The interval from 0 to 0.5, we're integrating 0 times cosine. I didn't even write it here because that's just going to drop out. That's just going to be 0. Plus the integral on the interval 0.5 to 2. This will not just simply be 0, so I am keeping it here. All right, so my x of t is just 2. That's what's going in here. That's the 2 here, times the cosine of n omega t. Cosine of n omega, which is pi in this case, times t. So the integration on this one is going to be easier than the first example in that if we look at what's inside the integrand here, I don't have a function of t times another function of t. I can pull the 2 out, in fact, and we're just integrating cosine of n pi t dt from 0.5 to 2. So the actual integration step or antiderivative step is simpler. I just need to integrate the cosine of n pi t. All right, so finding its antiderivative, the cosine, the antiderivative of cosine is going to go to sine. And don't forget, because it's not just cosine of t, it's cosine of n pi times t. So that n pi is going to come out when I do the antiderivative on this step. So the antiderivative is going to be that 1 over n pi sine n pi t. So I can pull that n pi outside of my evaluation here. So I have my antiderivative. Finally, I want to evaluate it between my bounds. So my upper bound is 2, so I'm going to plug in 2 for t. And then my lower bound is 0.5. So I can expand that out this way. Now we can simplify this down a little bit once again. We know from before, sine of 2 pi n, any integer multiple of 2 pi, this is always going to be 0. So that first term just drops out completely. We can actually see what happens here to this sine term. I can leave it as negative of sine n pi over 2. That's okay. But we do have also a periodicity here, although it's a little bit trickier, because when n is 1, it's going to be the sine of pi over 2. Then when n is 2, it's going to be the sine of pi. And then it's going to be the sine of 3/2 pi, and then the sine of 2 pi. So it is going to be alternating, but it's going to be alternating between, let me just make a little table here. So when n is 1, well, the sine of pi over 2 is going to be 1. I'll just call it my x value. When n is 2, then it's the sine of pi. Well, that goes back down to 0. 3, it's negative 1. 4, it goes to 0. And then 5, it goes back to 1. So this is only going to take values of 1, 0, negative 1, 0, 1, 0, etc. So there are ways we could simplify it down. Since we're going to be putting this into MATLAB for our use, I will for the moment just leave it as sine n pi over 2. But there are ways to simplify these types of repeating patterns down also if we wish. So I'm just going to leave it though as is, so that sine of 2 pi n term goes away. and I can just write my an terms as negative 2 over n pi sine of n pi over 2. Notice again here, and this is going to happen in our converging series, we have an n in the denominator, so these coefficients, the larger n gets, the smaller our an coefficients are going to get. And that should be expected because we have converging series where those larger n terms are going to have less and less an effect on our sum as we keep going. All right, we have our an. In this case, it's not identically 0 like we saw in the first example. And we can move on to our bn terms. Again, the process is basically the same, but we're substituting a cosine with a sine. Right, so that first step looks really exactly the same as what we have before. Now I can take my antiderivative of sine of n pi t. The antiderivative of sine is going to be negative cosine. Again, remember we have to use chain rule or really u substitution. And that n pi, we're going to have a 1 over n pi that comes out when we actually do the antiderivative. So we have a negative from going from sine to cosine when we take the antiderivative, and the 1 over n pi from that u substitution. So now my bn, I can expand out, evaluating it at the top, and then evaluating it at the bottom. Right, so when t is equal to 2, I have this cosine of 2 pi n, and I'm going to subtract from that my value when t is 0.5, or 1/2, a cosine n pi over 2. I did include the negative sign inside instead of the outside, so the negative I did distribute inside the cosine for this part, so that's where the negative sign went. And again, I can make some simplifications here. I once again have here this cosine of 2 pi n term, so again, any integer multiple of 2 pi, if I take the cosine of it, cosine of 2 pi, 4 pi, etc., that's always going to be 1. And if we look at this second term, we're going to have a similar type of pattern emerging for n equals 1, 2, 3, 4. When n is 1, it's the cosine of pi over 2. Well, that's 0, because that's 90 degrees. Then the cosine of pi, that's going to be negative 1, 0, 1, and then etc. So this is also going to have this pattern of being 0, negative 1, 0, 1. In this case, we're going to see that every odd n is going to, this term would drop out. But for the purposes of this, I'm just going to keep it as cosine of n pi over 2. When we throw into MATLAB, automatically that's going to come to light, that it's going to be oscillating between the 0, negative 1, and 1. But there are, again, ways we could simplify this further and get rid of that cosine term. So putting it all together for the bn term, I just put this negative 1 second. So I have this alternating 0, negative 1, 0, minus 1 inside the parentheses times this 2 over n pi. Right, I have my a naught, I have all my an terms, I have my bn terms. The bn terms also indicate we have convergence because the larger n is, the smaller these coefficients are going to become. So now I can put together my Fourier series expansion of my original piecewise function. Now again, we start with a piecewise function, and we're still going to get, in the end though, a sequence or a series of sines and cosines. Right, so putting in all the values that we know, we can write our expression like this with our, remember our a naught value was 3, so we have a 3 over 2 that comes out in front. We have this 2 over n pi in front of the an terms and the bn terms, so I pulled the 2 over pi outside of the series, so it's a little bit less to write inside. I had, just to refresh, let's just look at the bn. So remember I have this cosine n pi over 2 minus 1. Well, that's sticking around for this expansion. That's where this is coming from. That's from my bn term. And then I have sine of n omega t, that's coming out over here. And then that n, since it was 2 over n pi, the n had to stay inside of my summation, but the 2 and the pi, that was able to come out. So it's a little bit of a mess here. I have now cosine terms and sine terms. In the previous example, I only had a sine term, but I do have both of them in this case because my an was non-zero and my bn was non-zero. So it's a little bit a lot to look at here, but I have, at least for the infinite sum, I have perfectly recreated this piecewise function using only sines and cosines. And when using the partial sum, I am going to be able to, as I use more terms, as my big N increases, my estimate is going to get better and better and better as I use the first 100 terms or the first 1,000 terms or the first 10,000 terms, however many I want to use. We're going to see the estimate increases. The error goes down the more terms I'm going to be using.